In this tutorial, I will work two more proofs. These are, again, examples of proofs that use both inference and equivalence rules. So let's have a look at this proof in front of us here. Line 1 is P or Q. Line 2, Q or P implies R or S. Line 3, S or R implies not Q. And the conclusion we're trying to derive is P. So, again, I'm going to run through this process backward. I do want to remind you of one important consideration. Just because you do not get exactly the same proof that I get does not mean your proof is wrong or my proof is wrong. Both proofs may be perfectly adequate as formal proofs of validity because as they say, there's lots of different ways that we can pursue constructing a proof. So if you get a completely different proof than I get, don't despair. If you've used the inference and equivalence rules correctly, followed the rule of rigor, then you've constructed a formal proof of validity that just happens to be different than mine. So here's how I'm thinking about this one. So we need to conclude P. There's several considerations in the premises that we have, and I just want to point out a couple of things to you. First of all, the P or Q in line 1 and Q or P in line 2, those two expressions are actually logically equivalent. And if you review your list of equivalence rules, you'll see commutation is one of ours, and that basically just allows us to change the order of an expression when it's a disjunction or a conjunction, right? So these two expressions are logically equivalent, but so is the expression R or S and S or R. So it looks like we have opportunities to do a couple of commutations to make things line up so that the schemas exactly match, and that may enable us to do some additional things to this argument. So having said that, I'm going to add a different layer, and we're going to work this proof in a couple of different ways just to illustrate the point that there are multiple different avenues to get to a formal proof. So in this approach, I want to derive P. The most likely place to get P is something like line 1, where we have P or Q. Again, thinking of this disjunction, thinking of the inference rules that have disjunction in them, I think of disjunctive syllogism. So since we need P, if we had not Q, we'd be able to get P by disjunctive syllogism. Where would not Q be likely to come from? Well, if you look at line 3, we've got S or R implies not Q. So this has the makings of a modus ponens if we had the front end, which is S or R. Now look at line 2. We could easily have S or R if we do a little commutation and also modus ponens. So let's look. Let's say we have Q or P as the antecedent, and we have S or R. Now, I've done the commutation already, but we're just making notes here, so we don't. This is not a formal proof. We're just making notes to ourselves, okay? So have a look at this structure here. What we need is everything in this triangle, and what we have from line 2 is basically the beginnings of a modus ponens. So what would we need? We would need the front side, and that would be Q or P. But notice on line 1, we can get Q or P if we just do commutation. So that takes care of, I'm sorry, I wrote Q or P, P or Q. So if we use commutation, we can do modus ponens to get this expression, and then another modus ponens to get not Q, and then a disjunctive syllogism here to get our conclusion. So that's how we're going to approach this proof this time. So working backward, let's start on line 4 by writing Q or P. That's commutation on line 1. Now on line 5, we can apply that modus ponens to lines 2 and 4 and get R or S. That's going to be modus ponens on lines 2 and 4. Now let me pause for a minute and point out, we can't apply modus ponens to lines 2 and 1. Why not? Because consider the schema. The well-formed formula in the square has to exactly match the premise, the second premise of modus ponens. Even though we know that line 1 and the antecedent in line 2 are logically equivalent, that's not the way modus ponens schema works. We can't just say, okay, we can do that in one step on lines 2 and 1, because actually that involves two different rules, modus ponens and commutation. And the rule of rigor doesn't allow us to apply two rules to the same line for justification. So we have to do the commutation first to make the well-formed formula inside the square exactly match in both cases, and then we derive everything in the triangle. So that's the reason for not being able to collapse the modus ponens and commutation in one step. Okay, now that we have R or S, we want to do commutation again, and the way we did it in our notes to ourselves is we had the S or R, I think we did S or R, so that's commutation on line 5. And now on line 7, we can derive not Q, that's modus ponens on line 3 and 6. So again, here's the front end. The front end has to exactly match. That's why we did commutation. And we're entitled to conclude the consequence. So now we have not Q. Now we can use that not Q with line 1 to derive P by disjunctive syllogism. So that's just disjunctive syllogism on line 1 and 7. And because we have successfully derived our conclusion, the proof ends. Now, let's go to a new layer, and let's do a version of this proof that is different. It's going to follow basically the same outline, in the sense that, you know, we'll end up using not Q and line 1 to do disjunctive syllogism to derive P, but I'm going to give you an alternate way to get there. So on line 4, I'm going to do commutation like this. This is commutation on line 2, so you notice I've changed the order of that expression to make it like this. And then on line 5, I'm going to do commutation. R or S implies not Q. This is commutation on line 3. Now on line 6, I'm going to apply hypothetical syllogism. So how did I get here? So look at hypothetical syllogism. So something in a square implies a triangle. The triangle implies a diamond, and therefore the square implies the diamond. So the schema in the axioms is written as P implies Q, Q implies R, therefore P implies R. So we're just using that same approach, hypothetical syllogism on lines 4 and 5. What makes that hypothetical syllogism possible is the fact that we did those commutations in these steps so that the pieces, the antecedents and consequence, all match exactly. So now that we have our P or Q implies not Q, we're ready to do the step where we derive Q. How do we do that? Again, it's modus ponens on lines 6 and 1. So notice, here's the antecedent of the first premise of modus ponens. This is that antecedent on a line by itself. That's the second premise, and so we're entitled to conclude not Q. And then in line 8, we're able to derive P, and once again we're deriving P by disjunctive syllogism on lines 1 and 7, and the proof concludes. What these two proofs show is, once again, there are a variety of different pathways you can take in a formal proof. This one features a hypothetical syllogism. The previous one that we did, if I can remember what panel it's on, yeah, here we go. The previous one features two instances of modus ponens instead of that hypothetical syllogism. Which one is a better proof? They're both good proofs.